Hello everyone. Today we learn about the vector calculus. Previous chapter we has focused mainly on vector addition, subtraction and multiplication in Cartesian coordinate. Then we extended all these to other coordinate system. So in this chapter we deal with vector calculus, which is integration and differentiation of vectors. The concept introduced in this chapter provide a convenient language for expressing fundamental ideas in electromagnetics or mathematics in general. Of course, you feel uneasy of this concept at first and not seeing what they are good for, but student is advised to concentrate simply on learning the mathematical technique and to wait for their application in subsequent chapters. So this is introduce of mathematical techniques and we can apply further in the electromagnetic application in next chapter. So the differential length, area and volume. So in vector calculus, the important element is a differential length, area and volume. So differential elements in length, area and volume are very useful in a vector calculus. They are defined in the Cartesian, cylindrical and spherical coordinates. We look the figure. So in the figure we have dx, dy and dz. This is a cuboid. So how to find the differential displacement? So the differential displacement or dl means that differential displacement equal to differential of length. So dx in direction of x plus dy in direction of y plus dz in direction of z. So when we have a dl, we need to find the ds, meaning that ds is the differential normal surface area. So ds equal to dy dz in direction of x. Why? Because we took the surface between dy and dz. The direction of x must be perpendicular or normal to the surface. So dy times dz in direction of x, dx times dz in direction of y, dy times dx in direction of z. Differential volume is given by, so we have a three side x, y and z. So in differential term is a dx, dy and dz. So the volume is equal to the we time dx times dy times dz. As conclusion, we know that ds equal to ds at the normal direction. In this case, okay, for example, we took the surface like dx and dz. So what is the normal direction? An. An is a y direction. So the general equation is ds equal to ds times the normal direction. We look at the cylindrical coordinate system. So the cylindrical coordinate system is a rho, phi, and z. So we look this. In the coordinate system, rho, phi, and z. So when we have a rho, so we see that in the length differential of element displacement dl equal to d rho. So differential of rho in the direction of rho and differential of phi in the in direction of phi, but phi is variable with or dependent with the rho. So if they have a curve, if we call it rho d phi. So rho d phi in direction of phi and dz in direction of z. So dl equal to d rho in direction of rho plus rho d phi in direction of phi plus dz in direction of z. So differential normal surface area is given by, so we took the surface, the side surface. So first we took the side rho d phi and dz. So the normal surface is in direction of rho. Okay? So same with we took the side of dz and d rho. So the normal surface is in direction of phi. And same that we took the surface with a d rho and rho d phi. D rho and rho d phi. So the surface is dz. So the equation is to become rho d phi dz in direction of rho, d rho dz in direction of phi, rho d phi in direction of z. So the differential volume is given by rho d phi times d rho dz. The third one is spherical coordinate system. So spherical coordinate system, we know that is r, theta, and phi. So the differential element in spherical coordinates can be found as follows. So the differential displacement, so dl or length, equal to dr in direction of r plus r d theta in direction of theta plus r sine theta d theta in direction of phi. So look like this. So we see that so r dependent with the d theta. So r d theta in direction of theta and is a radius r is a dr and phi here is r sine theta d theta d phi. So this is r sine theta d theta, sorry, r sine theta d phi. Yeah, r sine theta d phi for this length. So for this length is r d theta. For this length, this length is only r. So the differential displacement is dr with direction of r, and another one is r d theta with direction of theta, and r sine theta d theta d, sorry, r sine theta d phi with direction of phi. So you can see that this is like this here. R dr with direction of r. So r d theta with direction of theta. This is r d theta direction of theta, and r sin theta d phi with direction of phi. This is the line of spherical. So the differential normal surface area is we taking that the side r sin theta and d phi and with the surface with r d theta. So the normal direction is r direction. So we took the surface r sin theta d phi and dr. So the normal surface is in theta. So we took the surface dr r d theta, and the normal direction is the phi direction. So the differential volume is, we time all. So dr time r sin theta time r d theta. So we can get r square sin theta dr d theta d phi. So look at example. Consider the object shown in figure 3.7. So this is a figure 3.7. Calculate the length BC, the length CD, the surface area ABCD, the surface area ABO, the surface area AOFD, and the volume the volume ABDCFO. So from the surface, we can see that. So the coordinate is Cartesian, but the figure show the cylindrical. So what the first step we need to take is that to change or to transform the Cartesian coordinate to the cylindrical coordinate. So we take one by one point. So at the point A, phi 0, 0, when we transform using the coordinate transformation formula, so we can get phi 0 degree 0. With point B 0 phi 0, we get pi over 2 0. C 0 phi 10, we can get pi over 2 10. And T is phi 0 10, we can get pi 0 degree and 10. So when we change to the cylindrical coordinate, and then we can solve the question. So A is along BC. So you can see that along BC. So along BC, the DL, the length is located at the Z. So the length located at DZ. So BC is equal the integral of length DL. So DL equal to DZ. So the limit is, we took the z coordinate. So from 0 to the 10. So dz equal to 10. So along CD is a curve. So CD is a curve. So DL, if curve in the cylindrical coordinate is a rho d so the integral of rho d phi. So rho is a 5. So integral d phi, we got the phi. So d phi here is how much? So d phi here is pi over 2. From 0 to pi over 2. So we can get 2.5 pi. For ABCD DS, we took that. So DS ABCD. So A, B, C, D. What is the surface here? A, B, C, D. So the DS is, if A, B, C, D, mean that, so the one side is a D Z. Then this is another side is a rho D phi. So rho D phi D Z. So rho d phi, because a curve, and this also dz. So times dz. So you can integral. So ds equal to rho d phi dz. So the limit of dz is from 0 to 10. The limit of d phi is from 0 to pi over 2, and rho is a pi. So you can get the 25 pi. Same as with the ABO, AOFD, and the volume you can multiply all rho d phi dz d rho. Okay. Now we learn about the line, surface, and volume integral. So the familiar concept of integration will now be extended to cases in which the integrand involves a vector. By line, we mean the path along a curve in space. We shall use terms such as line, curve, and contour interchangeably. So the line integral of length with a vector A times dl is the integral of tangential component of A along curve L. You look like this. So the integral along of the length, which this is the line integral. So the integral of length A vector A dot dl. So we call it the electrical flux. We need to find electric flux for the application of the electromagnetic. So the final answer after the derivation is a flux equal to the integral of A cos theta d theta equal to vector A dot the normal direction of ds. So the flux equal to integral of s vector A dot ds. So you can uh, study the example 3.2 by your own, and you can see how the line integral application. So you derive one by one, you will get the answer. Thank you.